recording and then I'll have to sharpen up. Okay. For a little bit of review. Oh, my pen's a little. We did long division of polynomials, which was super fun. Of polynomials, where we did things like if we have p of x divided by, now let me see, divided by d of x is q of x plus r of x. Pretty sure. Can never remember the order. I know the remainder is r of x. Yeah. So we have some polynomial, and then I promised that we're just gonna go to and divide by things like x minus c. And then we have the factor and remainder theorem, which are pretty straightforward. The only crazy one is the remainder theorem. It's a little bit crazy, I guess. If you have some c, right? So you're dividing by x minus 3, for example, then what can you do? You can check that you have the right remainder after you've done all your work by plugging in p of 3, right? Whatever your c was, make sure that you have it in the form of x minus c, right? And then you can check that you have the correct remainder, because p of c will be the remainder. Okay. So, bless you. The remainder theorem says if d of x, and I guess it depends on what textbook I use capitals here, but lowercase is fine too. If I'll be consistent, d of x, I'll say, or dx, d of x, whatever. From last day is x minus c, where c is a constant. Whoops. We can check that we have the right remainder. We can check that we have the right remainder by finding p of c is equal to r of x. And maybe I'll put this p of c downstairs. Now I overstepped, I think. Wanted to show you that you can do anything, and you can, but in terms of what I'm expecting of you on a test, let me get to those exercises and grab one. What I'm expecting of you, oh, come on. Maybe notes. Something like just little like this. Oh, those are my notes to myself. Decided not to do that one. Right, so as promised, just dividing by something like x minus c, right? And so let's do this one as a little bit of review. Okay. You can handle bigger things in the divisor. You can. You do the same thing, but for the factor and remainder theorem, we have to have x minus c, and so that's as far as we're going to go. So what does this look like? This looks like x minus 3 into 4x squared plus 3x minus 1. All right, still a little early, right? But still will get you warmed up quick. 4x squared divided by x puts me at 4x. And then I divide it back down, or sorry, multiply it back down, 4x times x minus 3. And I put it down below here, making sure that we stack our x's, our appropriate powers of x's. And I checked, but I didn't say I checked, right, that we have decreasing powers of x. So even if you have a coefficient of 0, I would include it there as a kind of a placeholder. Okay. But in our case, we have x squared, we have x to the 1 and x to the 0. So the gang's all there. So now we take 4x times x minus 3, putting us at 4x squared, which is a good start, right? Because it's supposed to go away. 4x times negative 3 puts me at minus 12x. And then I have to subtract that from the top. Now I'm not writing the minus 1, but we can bring it down, and I do, just because it makes it look a little bit more focused. So I get 0, and then 3x plus 12x puts me at plus 15x. And then minus 1, I bring it down. You can bring it down at every step, but that feels like a lot of writing. Or you could not bring it down at all and just remember that it's there. That's up to you. But now we do the same thing with 15x minus 1. So now we have 15x divided by x, puts me at plus 15. And then I multiply the 15 times x minus 3 back down. Okay. So now I have 15x, and then 15 times negative 3 minus 45. Is that true? Okay, thanks. Subtract that. This goes to 0. That's good. Negative 1 plus 45 puts me at plus 44. Which is my remainder, right? And so one of the things that we said was, okay, if we're dividing, so if our d of x is something like this, so our divisor is x minus 3, which means that c is equal to 3, by the remainder theorem, oops, so weird looking b. By the remainder theorem, p of 3 must be equal to 44. Where remember that this is p of x, your original polynomial. Okay. And I'll put this here, d of x. So we can check it. Let's see here. P of 3 is, try to have them on the same screen here, 4 times 3 squared plus 3 times 3 minus 1. Math. Times 4, so I get 36 plus 9 minus 1. Phew. 44. That's good. Yeah. So that means that we can feel really good about our calculations up above, right? Because we got a remainder of 44. And let's see here. So then r of x is equal to 44. And finally, see, what color haven't I used? Q of x is 4x plus 15. Oops, that's not very nice. You know what? The whole thing was not very nice. There we go. Plus 15. What does that mean? It means that we can rewrite 4x squared plus 3x minus 1. We can rewrite it. Okay, here we go. Therefore, p of x divided by q of x, or sorry, d of x is q of x plus r of x. Good. So then, what's our p of x? 4x squared plus 3x minus 1. 4x squared plus 3x minus 1 divided by x minus 3 is equal to q of x, which is 4x plus 15. I'll put brackets around to show that that's one thing. And then plus the remainder, which is 44. Cool. That's a skill. Yeah.
So on a test for these kind of questions, is it going to be asked like find r of x of this, or is it just like do division?
I know the assignments are asking for find what's q of x and what's r of x. So I'll do the same thing just to kind of mirror the setup. But it'll be set up similar to the assignments in the sense that you have this p of x, d of x, and then part 1, find the quotient, find the part 2, find the remainder, confirm part C or part 3, I guess, switched ordering styles. Confirm the remainder using the remainder theorem, which means you have to remember what the remainder theorem is, right? But that's this little guy here, right? And it's really just a way of checking your work. That's a solid question, huh? Just have to, nothing to it but to do it. And pretty fun, right? Polynomial long division, tedious. I love tedious things because it makes me feel like I know what I'm doing. Okay, yeah. Do that, do this, do that. Any questions about polynomial long division? No. We're warmed up though, huh? Okay, I'll call that the end of the review. And as a side note, we're not doing, so that was 3.4, and now we're skipping straight to 3.7. So we cut a bunch of sections, which might be of interest. Things like complex numbers, so imaginary numbers, that kind of thing. We're skipping that. But if you are interested, then, right, if you take the square root of -1, it turns into I, which is an imaginary number. But you don't need imaginary numbers, so we're skipping it. Okay. So, note, skipping to 3.7. What's 3.7 called, I wonder? And did I make a note on there? Because I do not want to be scrolling around forever. I didn't. How about bookmarks? Nope. Did not set myself up at all for anything good. Okay. Rational. Trying to remember. Ha. There. And I'm gonna sneak a bookmark there. So I don't have to do that again. Okay. Oh, there's this keyboard that you can't see, but it's driving me nuts because it's all in the way. How do I hide it? Oh my gosh. Hide keyboard. Then it shows a bigger one. Okay. Okay. The last section in this chapter is on rational functions. Now, so there's a lot of things that we could talk about in terms of rational functions. I want to do just the quick and dirty version of rational functions. And so rational functions, oh, it's got those highlights that I don't want, but I don't know how to get rid of them. Just all the B's. All right, ignore that. Sorry. Okay. Copy that in. Rational functions are when we have things like a polynomial divided by a polynomial, right? And now today we want to talk about how the graphs behave. And there's a lot of behaviors, but we're just going to talk about the most important things like the vertical asymptotes and holes in the graph. Okay, so when we have things like, so a rational function is when we have some p of x divided by, and I'll say q of x, right? Two polynomials, one in the numerator and one in the denominator. So these are both polynomials. One of the things that's going to happen is q of x might be bigger than p of x, bigger in the sense that the degree is higher, right? And so then in the long run behavior, what's going to happen is you might have something that looks like 1 over x, right, in the long run. Now 1 over x looks like, and let me just grab it. Both of them. Although when I did that bonus, I saw that there was some 1 over x. I think there was even a 1 over x squared that you remembered, which is pretty fun. Yeah. So if you have something where p of x is degree, can I go there? Degree n, and q of x is degree n plus 1, right? What's going to happen in the long run is it's going to approach 1 over x, right? Because you've got one more x, right? One more x degree in the denominator than you do in the numerator. And so overall for the long run behavior, you get something that looks like this. Okay? Now, one of the things that we're going to talk about today that I'm not skipping are these vertical asymptotes. We also have horizontal asymptotes, but I want to focus on vertical asymptotes. It's the first time I'm writing it. I don't know why I did it so sloppy. Haven't introduced it really. A vertical asymptote. Okay. If we take a step back and we look at just 1 over x, we know that the domain of 1 over x, we know that we can't divide by 0. And so x equals 0 is not in the domain. All right. Here. notice x equals 0 is not in the domain. So it makes sense that you have no values at x equals 0. Okay? Now what we have is this kind of, right, going to infinity as we get closer and closer to x equals 0. Now, some of the notation that we're going to use is we're going to be approaching x equals 0 from the left, okay? Because that behavior in this case is going down to negative infinity. But if we approach x equals 0 from the right, then we have a different behavior, right? And so we need to specify which direction we're coming from. So we say, we usually do, now I'm blanking here, and I shouldn't write it there. Anyways, let muscle memory take over. X approaches 0 from the left. There. So here, I did it. This says, as x approaches 0 from the left or from the negative side, that's fine. But so here, as x approaches 0 from the left, f of x approaches negative infinity. Now, we can do the same thing as x approaches 0 from the right, right? And so now we're going to have different end behaviors, or sort of asymptotic behaviors. And as x approaches 0 from the right, so we use a plus from the positive side, but for some reason, I use left and right, but positive negatives work too. So as x approaches 0 from the right, f of x is going to positive infinity. I'm going to do my infinity like you guys told me to do, but I hesitated down here. Uh-oh, a little wonky. Yeah. So we get this vertical asymptote wherever the x is not in the domain, right? Because it can't be there. And so one of the things that we'll see is that in this case, there is no vertical intercept, right? One of the things that we've been working on are the vertical and the horizontal intercepts, right? But there is no way or nowhere that it can cross x equals 0 because it can't be x equals 0. So this is one of those cases where you're not going to have a vertical intercept, and that can happen. Okay. This is called the reciprocal function, just as a which means that this is the reciprocal squared. One over x squared. Well, looks similar, right? Except now x squared turns all the x's, even if they're negative, right, makes them positive, and it really just flips this up to the positive y's, right? And so it does similar things. X still can't be 0. 0 squared is still 0, right? And so here again, we have a vertical asymptote. Vertical asymptote at x equals 0. Since x squared equal to 0 means that x is not equal to 0. Whoops. X equal to 0 is not in the domain. Let's do the same thing. So as we approach this vertical asymptote or the thing that's not allowed in the domain, right, then we can approach it from the left and we can approach it from the right. And so we can do the same thing, but in both situations here, they're just going to go to infinity and they're never going to touch x equals 0 because they can't. Oops. As x goes to 0 from the left, f of x goes to infinity. Ooh. Ooh. And as x goes to 0 from the right, f of x also goes to infinity. I'm like focusing on my infinities today. Except my first one, it was a pancake. Pancake. I'll get there. Okay. All right. So let's see here. I haven't been using these in a while, have I? Well, we did those. Let me scroll since we're skipping sections here. Oh, looks familiar. Here we go. Put a fresh page here. Okay. We want to find the vertical asymptotes of these two functions. So these are rational functions, right? I've got a polynomial over a polynomial. And so we can handle that. This is also a polynomial over a polynomial, right? It's just in factored form, which is really a lot nicer, I think, right? Because then you can look at this and set x equal to -1 and x equal to 2, and both of those will give you vertical asymptotes. There, I've given it away. Spoiler alert. Let's do this one first. Okay, so here, I'll just make a note that these are both rational functions, a polynomial over a polynomial. The rules are the same as before, right? And so knowing that vertical asymptotes happen at values of x that are not in the domain, let's write that down. I'm saying happen. It makes sense to think of them as they happen, but I have to put it in quotes. It's not really proper. But vertical asymptotes happen at values of x that are not in the domain. Which in our case, if we just have a fraction, then we're only really concerned about where does x squared minus 7x minus 8, where is x equal to 0? Or where does this equal 0? Sorry. So here, right, this cannot equal 0. One of our go-to moves, I see a quadratic, And right away, I'm just going to use the quadratic formula, right? I'm not going to mess around with things like what adds to -7 and multiplies to -8 because I don't like it. I guess it's kind of staring me in the face, but I don't want to, right? And so for me, if you can see this, right, what adds to -7 and multiplies to -8? Probably -8 times +1, -8 plus 1. Oh, dang, it works. But if you're like me and you don't see that right away, that's okay, right? As long as you have a quadratic, you can use the quadratic formula. Okay, so let's just focus on this little guy for a little bit here, or for a long bit. We're here for a good time, not a long time. So we need to set x squared minus 7x minus 8. I'm going to force it to be 0, find the values that make that happen, and then go from there. Can be solved using the quadratic formula. The beauty of a quadratic. Surprise, surprise. The quadratic formula is that x, so if we have a quadratic set equal to 0, the values of x that make that happen is -b plus minus the square root of b squared minus 4ac divided by 2a. You probably have that memorized already, but I'm sure it's on your formula sheet somewhere. Just haven't looked at it in a while, so I don't know where. But it's usually on there. Okay, so we have a is 1, b is -7, and c is -8. Thank you. So we have x is equal to -7 plus minus the square root of -7 squared minus 4 times 1 times -8. Right, I'll just make a note here because it's been a while, I guess. But for me, the quadratic formula is like my best friend because because I don't see the factors. I don't have it. I don't have that magic. And that's okay. I don't need it. There. A little bit more work, but it will always work. Okay, so I get 7 plus minus, now let's see here. 49 minus 4 times -8. It's important. Puts me at 81. The root of 81, which is a nice value, surprise. So I get 7 plus minus 9 divided by 2. I'll do the minus part first. So I get 7 minus 9 is -2 divided by 2. And I'm really emphasizing that comma because there are 2 values, right? 2 solutions. And so 7 plus 9 divided by 2 is, oh, I went too far. 7 plus 9 is 16 divided by 2, which means that we have -1, so x equals -1 or 8. I feel like I said -8 and +1. I shouldn't have outed myself like that. See, I don't have the gift. I have to use the quadratic. Okay, So how do we use this? Now I can use these x equals -1 and x equals 8, and I can rewrite. So if I wanted to, I could rewrite this, right, as in factored form, which is a lot easier to work with, right? And so what we have to remember, and you don't have to rewrite it in factored form, right? We already found that the values of x that set this equal to 0 is -1 and 8, right? So we already found the values of x that we cannot have, right? That are not in the domain, right? But just as an exercise, I'm not going to try to memorize this for this quick scroll here. I want it on the same page, but it's going to be weird to go back up here. But if x is negative, oh, I do have the magic. It just takes me a while. If x is -1, then the value is 0, right? And so what I'm going to have is I'm going to have x plus 1, right? Because, and just check in with yourself. If I force x to be -1, -1 plus 1 makes 0, right? So then I'm on the right track. And in a way, you're just kind of doing the opposite sign of what you have in your x times x minus 8, right? Because if I let x be 8, this thing is supposed to be 0. So now I've rewritten x squared minus 7x minus 8 as x plus 1 times x minus 8. And now, in my world, it's easier to see from the factored form that, okay, x equals -1 and x equals 8, those are not in my domain anymore. Okay, so here, therefore, x equals -1 and x equals 8 are not in the domain. Oops. Trying to keep it on the same page, but I wrote so lofty up here. Are not in the domain. Too lofty. Okay. So that means that we have vertical asymptotes at x equals -1 and x equals 8. Okay, you know what? I'll just go across. Therefore, there are vertical asymptotes at x equal -1 and x equal to 8. We don't know what the behavior is yet, but we were just asked to find the vertical asymptotes. But let's confirm it in Desmos, just so we can see what it looks like. Oh yeah, what did we find last day? Let's see if it works in this one too. If I put it on this side, then you can see both. But if I put it on the other side, you can't. Okay. It's tiny. I'm just gonna graph f of x. Okay, making sure that you keep your numerator together. I like to use brackets just to emphasize. And so here we go. X squared minus 4 and bracket divided by, and it should step it all down. And then I can do x squared minus 7x minus 8. Whoa, Crazy. Looks good though. Right? Here, this looks like -1 to me. Right? So we've got this asymptotic behavior, a real asymptote. And then here at 8, I'm assuming 8 because that's what we found, right? And so we did good. We did good. How can I save? Bring them in here. What? Oh, oh my gosh. Don't get seasick. There. Oh, whoa, cool. It turns it into an arrow. It's not what I wanted, but neat. X equals, whoops, -1. And here, 5, 6, 7, 8. And a 1 and a 2. So it looks good. That's all we had to do for now. All right, let's do the next one. Gonna snag it. Oops. Oops. Doesn't need to be that big. There. So we're trying to find the vertical asymptotes again, but when it's in factored form, it's a lot easier. Right? X equals -1. Or I guess I could say X is not equal to -1, right? Whatever you prefer. And X equal to 2 are vertical asymptotes. That was easy. Can confirm it, right? Because the 3 is never going to be 0. Anything multiplied by 3 is never going to go to 0. So you don't have to worry about the 3. It's the X plus 1 that can go to 0. The X minus 2 that could go to 0, right? And let's just graph this here. Same thing, I use brackets to keep my numerators all up top. X plus 3, and then I can divide by, good, 3 times X plus 1, bracket, bracket, X minus 2, bracket. Ta-da! Now we've got this kind of strange behavior, but that's okay. How do I? Just bring it in so we can see it. I'm gonna crop it up. Don't need that much. So again, here, if I zoom in, right, if this is -2, this must be -1, which is good. And then we found at 2, which looks like it's also going to check out. Pardon? Oh, this piece. So that one's just kind of wedged in the in the middle, but it looks like a parabola, right? And so, and it is. So it's just gonna be from these parts. We're gonna get there. This is at x equal to -1, and this is at x equals, oh, I didn't. It's supposed to be at 2, but whatever. Okay, good. Let's see here. Should I go to the example right away? Let's do this one. Show by example. So again, we want to find the vertical asymptotes of x plus 3 over x squared plus 4x plus 3. Now, right away, right, I can't be bothered, right? And so I'm just going to use the quadratic and to factor this thing, because that way it'll be easier to see and just easier to represent this function in factored form, right? And so let's do that first. Use the quadratic formula. To write it in factored form. I wonder if your calculator, does your calculator have a fancy quadratic formula? It does. Nice. Okay, that's good. I'm doing the work like a chump. That's okay. I'm all right with that. So if I enter this in the calculator, it'll do it? Oh, yeah. Let me try. X plus 3, step it down. My brackets. How do I use a snack calculator? Oh. I'll kick it old school. X is -b plus minus the square root of b squared minus 4ac to it. In this case, a is 1,